Hello, welcome to Cosmology Talks. Today we have a bunch of people from the Atacama Cosmology Telescope talking about their latest lensing results with cosmology as well. So the people are Dongwon Han, who is a postdoc at Cambridge, Blake Sherwin, who is faculty at Cambridge, Mathew Madhavacheril, who is a faculty at the University of Penn, Frank Qu, who is a PhD student at Cambridge, and Niall MacCrann, who is a postdoc at Cambridge. Yeah, so as I said, they're talking about the ACT Cosmology lensing results. One thing I'm really keen to hear about from this and discuss with them perhaps is why their S8 results seem to match other CMB experiments more than they match other large-scale structure ones, because naively I thought that cosmologically that's what they'd be sensitive to is the local structure, but they seem to match the CMB, which on an even more naive level maybe is what you expect because they are a CMB experiment. But yeah, one step of less naive, I'd have expected they match large-scale structure, and they don't. So very keen to hear about that, but I'll let them start where they want to start. So welcome, everybody. Do you want to start by telling us briefly about the paper or group of papers?
Thanks, John. So we have made the state-of-the-art CMB lensing measurements over 9,400 square degrees of the sky using new data coming from the Atacama Cosmology Telescope. And this derives in one of the most precise lensing power spectrum measured up to date, and we can use it to constrain structure growth by measuring S8 and sigma 8 when we combine that with external data sets like PAO, and we find great agreement with Planck and also with lambda CDM.
Cool, thanks, Frank. To everyone, if people are thinking of this talk or your papers 6 months from now or a year from now, and they can only remember two or three things, what would you want those two or three things to be?
Yeah, so I can start. Firstly, we're showing here that we can do CMB lensing at really high precision with ground-based data, with a ground-based telescope. Our precision's very close to what Planck had, and that it basically shows that we've dealt with the extra systematics you have from the ground, and it's a really good sign going forward to when we're going to get a whole lot more data from ground-based telescopes with Simons and CMBS4. And the second one I would say is, we found a result that really supports lambda CDM and the standard cosmological model and the Planck primary CMB. And if there is an S8 tension, we're not seeing any indication of it, and that implies that it would have to be coming from quite low redshifts or from small scales that we're not probing with CMB lensing.
Maybe for discussion later I can dive down on the word if in your statement about if there is an S8 tension. Yeah, so why did you guys do this? You've got the telescope, you've got the data, but what is unique about kind of ACT compared to Planck and other CMB experiments? Why is the lensing interesting in and of itself instead of just the primary CMB? What is special about this particular analysis now in 2023 instead of what ACT has put out in previous years with lensing, and what other kind of background motivation should we be aware of about the work?
So I think the very short answer is just CMB lensing generally is a very powerful probe of the projected mass distribution of parameters that are probed by structure growth, such as neutrino mass, and so making a state-of-the-art high-precision measurement of this probe, which is very robust, is generally very interesting. But as you indicated, right now this is a particularly interesting and pressing topic, right? Because everyone is trying to understand what is going on with the S8 tension, and we think that we can clarify to some extent what is going on, or provide some insights at least. Yeah, so I'm sure everyone who would be watching this video knows, why it's interesting to map out the dark matter and mass, right? How the mass is distributed contains a wealth of information about cosmology. And, our work focuses on the lensing of the CMB, which has sort of unique properties. First of all, it's the most distant source, and so it's great at probing high redshift distant mass. But it's also a particularly well understood source, right? And so I think it's very complementary to galaxy lensing in the sense that we really understand the CMB source. We know exactly what redshift it comes from. We understand the sort of linear physics of the CMB source really well, which makes it quite a robust probe. And so, the effect we're dealing with here is what you would expect. The CMB photons travel through the universe and they're gravitationally lensed along their paths by just an arc minute or two. And so the effect, just to give people a reminder of this lensing on the CMB, can be shown here. This is a really exaggerated picture where you see the impact of having a really exaggerated blob of mass on the background CMB fluctuations. And what you see is that the CMB fluctuations behind this blob of mass are magnified and sheared in this characteristic way. And this defines an observable, this remapping the lensing deflection field or the gradient of the lensing potential grad phi. And so we can map out this lensing potential, or equivalently the lensing convergence. Okay, so that's sort of the first thing you get from a lensing pipeline is you get these lensing maps. But our measurement focused not just on these lensing maps, but also on the lensing power spectra. And this is really the key thing, the key observable we'll be talking about, the power spectrum of this lensing map, which tells you the strength of lensing as a function of angular scale. So this is CL phi phi. Now, just a reminder, where the shape comes from, of course, the lensing map probes the projected mass, therefore the lensing power spectrum probes the projected matter power spectrum, right? So you're just seeing this matter power spectrum in projection, and that's where the shape is coming from. In case it's interesting for people to remind you why this is a cool observable and why it's a little bit different from other lensing observables, the signal is coming from quite high redshifts, right? So you can see the redshift origin in this plot, where you can see how the lensing power spectrum is built up from different redshift ranges. And so it comes from a broad range of high redshifts, with the mean redshift at redshift 2. So it's quite high. And it also is different from galaxy lensing experiments in the scales that it's probing, because we're probing either linear scales or just barely nonlinear scales. So we have very mild sensitivity to nonlinear scales beyond cave around 0.2. So it is somewhat different in what we're probing. But just like galaxy lensing, we are probing, again, primarily two parameters. We're probing sigma 8, right, the clumpiness of the universe, and omega matter. And you get this well-known degeneracy between these two parameters. There is a difference in detail, though. We're not probing the same S8 as galaxy lensing. We're probing S8 CMB lensing, which is sigma 8 times omega matter to the 0.25. So the exponent is different, and that's because it's at a different redshift. And so this is obviously a generally interesting probe of anything that affects structure growth. For example, this is a great way of measuring neutrino mass, etc.
I wonder if we can just kind of unpack a little bit what you mean when you say you probe a different S8. I mean, everyone probes all S8s, but the point of S8, if I remember correctly, is meant to be where you essentially make the final contours as circular as possible, so that there's no degeneracy. And so what you mean is that the S8 that makes your contours circular is this one, but you could still quote S8 that Dark Energy Survey or KIDS or HSC use.
Exactly, yeah. We could. The problem is that, you could imagine the galaxy lensing contour would be just a little bit slanted in a slightly different direction, have a slightly different slope. And so, they would not constrain our best constrained combination very well, and we would not constrain their best constrained combination very well at all. So in order to overcome this, we combine with BAO. If we want to constrain their best constrained direction, we combine with BAO that pins omega matter, and that allows us to do an apples-to-apples comparison. You can also do agnostic tests of how structure grows and how, whether there's some sign of new physics in structure growth or not. And I'm sure most people watching this channel will know about this very powerful test of structure growth, right? Where you fit a lambda CDM model to CMB power spectra at redshift 1100 and then predict how structure grows down to redshift 1 or 2. So you predict S8 or sigma 8, and then you compare this prediction, which assumes standard physics, with what you directly measure at low redshift, right? And this is generally interesting to do, but of course now it's particularly interesting, next slide, because of the S8 tension, right? Because there's signs that something is sort of wrong with this predicted structure growth versus what we actually measure. And so, here's a typical summary plot that you've probably seen before. In green, you can see the sort of predictions from extrapolating high redshift CMB power spectrum fits down to low redshift. And in blue, you can see measurements from mainly galaxy lensing surveys. And, as I'm sure everyone knows, it's not that any one of these is really in significant tension, or in that significant a tension with the Planck primary CMB power spectra, but it's just that there's several probes now that are coming in a bit low that starts to make this quite intriguing, this picture. Yeah, so where does CMB lensing come into it? Well, so we will be able to present a measurement of S8 or sigma 8 or these combinations that's really state-of-the-art precision, right? Competitive with anything else. 1.6% to 2.7% precision, but it comes from an entirely different channel, right? So it doesn't depend on galaxy surveys at all. It has completely different systematics from galaxy surveys, and it's also to a large extent, although not 100%, independent of Planck. So it'll also provide a valuable cross-check of systematics in Planck to a significant extent. And so that's, I think, very interesting if you want to figure out, are these fluctuations that we're seeing here that are really weird fluctuations? Or are these systematics, or are these first hints of new physics, right? Of course, the most interesting scenario would be if this is really new physics, not just systematics.
How independent are you of the actual primary CMB anisotropy? Because you said, I guess, obviously correctly, that on the theoretical side, we know the linear expectations of the CMB fluctuations. And then, of course, what we see is the lensed image of that. One can imagine that if we didn't understand linear CMB anisotropies for some reason, if there was some new physics there, that one could infer that something was lensed when something else has happened. Or I don't know, I'm just kind of putting my speculation hat on. What do you have in terms of thoughts on that?
Yeah, so really what we're really measuring is a combination of the lensing and the primary CMB. But the thing is that the primary CMB is determined so much better, an order of magnitude better than the lensing, that you'd have to get something, catastrophically wrong, like at 10, 100 sigma with your primary CMB measurements for it to mess up the lensing, right? So I think to a large extent you can say that we're independent of the primary CMB. There are other interesting phenomena that occur, like you can make a mistake in your overall calibration and it won't mess up the lensing. There's some subtleties, but I think the big picture argument is just, you don't have to really understand the physics. You just need to know to a reasonable approximation what the power spectrum measurement looks like.
I guess what I was meaning in a kind of like toy model proof of concept kind of way. I'm not saying this is realistic, but just if there was something really weird at the last scattering surface that looked like lensing today, I don't know what it was, but it looked like lensing today. Then in some sense, there's some new physics going on that you're not 100% independent of, but I don't know what that could possibly be.
What you would have to have is basically what we're looking for, and we'll go into this in a second, is breaking of isotropy across the sky. So, some directions are lensed, some directions are not. So if there's some other reason why the CMB happens to be varying across the sky in a way that looks exactly like lensing, but with the wrong amplitude, then you could do this. But I think that's first of all, I've never seen anything like this before work. And also then you wouldn't be able to explain all the cross correlations that we see working very well. So I think it would be interesting to think about, but I don't think it's very easy to do. Yeah, so obviously the most interesting thing, and I think you were asking about this, Sean, is how this measurement can kind of inform if new physics, if we believe that this might be the explanation. And it's worth emphasizing, again, that all these probes, even though we're quoting S8 or sigma 8, they're all really generally measuring different things. They're measuring structure growth or the matter power spectrum in different redshifts and on different scales with different wave numbers, right? And I've sort of kind of sketchily illustrated that in this plot here. So what we can particularly test and rule out or confirm is whether there's any new physics that suppresses or affects growth of structure between redshift 2 and redshift 1100, by comparing our S8 with primary CMB1 on larger scales. But, there's a whole interesting field, and I think Matt will talk more about this, that that doesn't mean that these other measurements are necessarily wrong. It could just be that that's happening on smaller scales or lower redshifts than we're accessing. And so that'll be really interesting to compare further.
Thanks, Blake, for the background. Shall we get into the details then? What's specifically new about this series of papers, and what were the S8 constraints in the end?
All right, so I think we're all going to present about that. And so the papers that we put on the archive the other week are the ones that you can see there: Qu et al., Madhavacheril et al., MacCrann et al. And so broadly, we'll just discuss the CMB data, the CMB maps that we used, then the lensing maps, and then our lensing power spectrum measurement. And finally, we'll discuss, the parameters and the conclusions. So Dongwon will start us off by discussing the CMB maps.
So I will discuss the CMB maps on the behalf of SIGARDNESS. So here's the ACT collaboration. We are about 160 collaborators across 45 institutions. So Atacama Cosmology Telescope is a high-resolution millimeter wave survey located in Atacama Desert, Chile. As you can see on the right side of the plot, there are a number of astrophysical and cosmological surveys in this area. That's because Atacama Desert, due to its high altitude and very dry weather, is one of the best places for cosmological observation. And Atacama Desert has been operating here from 2007 to 2022. The current data set is ACT DR6 dataset, data release number 6, and it came from the advanced ACT configuration, which makes observation from 2017 to 2022. And the top plot shows the depths of our observation across our footprint. And we measure about the 46% of the sky with a medium depth of 10 micro-K arc minute. And this is about 10 times more constraining than our previous cosmological dataset, which was a ACT DR4 dataset. So for this particular set of lensing analysis presented in this 3 paper, we used a subset of data from the ACT DR6 dataset, which is called a nighttime dataset. That is because a nighttime dataset is easier to characterize a beam. It has much nicer systematic. But this is still 2/3 of our total data volume, and as a result, it's about 6 times more constrained than the DR4 release. So this is still quite an improvement from our previous analysis.
When you say 6 times as constraining, do you mean there's 6 times as much data and therefore, I guess, square root of 6 times as large statistical error bars, or 6 times smaller?
I think it's a square root of 6. So 6 times the data volume, hence, it goes like a square root of n.
There is a subtlety, though, that if you're looking at higher point statistics, it scales down a little faster, right? Like the power spectrum will scale down just as like the data volume if you're noise dominated. So it sort of depends. I think I agree with DW, but there's some subtle.
And then it also turns out that we're signal dominated on many scales, so it doesn't scale as fast as that because of the factors. So, there's multiple factors, and it's a little bit hard to predict if it's going to be 6 times or square root 6 times better. But I think the 6 times here refers to the total number of time-ordered data chunks that we have, essentially how much time.
Total observation time, basically. So here is an example of ACT DR6 map. On the top panel, you see the total intensity, and the bottom panel, you see CMB-E polarization mode. As you can see, even just with the eye, is that ACT measurement is quite signal dominated. And because lensing performance scale with a number of signal dominant mode, ACT with a large area and high sensitivity make it particularly powerful data set to do lensing analysis with.
Can I just quickly properly understand when you were talking about this scaling of noise, when I think Matt said that you're signal dominated, you're essentially meaning that then the actual dominant noise is cosmic/sample variance, that like you actually know what the actual temperature and polarization is on each pixel, and and so therefore measuring it better is not, I mean, it's helping a little bit, the instrumental noise is dropping a little bit, but it's not the dominant noise. I see.
So you might not improve on certain scales and temperature, but the polarization is almost always noise dominated up to a certain point, and then you start getting more information from polarization. So we use both temperature and polarization, right? So it's a little bit hard to predict.
Right. So this is just a 1-minute interlude where I'll just quickly go through how we measure lensing, and then I'll turn over to Matt, who'll discuss our lensing maps. So we have these CMB maps, and we'd like to measure lensing from them. How does that work? So the algorithm we use is what's called a sort of standard quadratic estimator, which basically measures new correlations induced by lensing between 2 different modes of the CMB temperature and polarization sky. And so you can see here this integral over different pairs of modes. That's not all that intuitive, though. So, can you get some intuition for what this quadratic estimator is actually doing? And at least in some limit, it's pretty easy to understand. So basically what this quadratic estimator is doing is it's locally measuring the power spectrum in little patches of the sky. Okay, and if you're looking at a direction, if you're looking at a patch where the CMB has been magnified a lot more than average, then that local power spectrum, that local 2-point function, will be shifted to larger angular scales than average, right? And that's how you know that direction has been magnified, right? Because that power spectrum has been shifted to large scales. And so in that way, you can go from a map of the CMB to a map of the lensing. And that is what we will talk about, what Matt will talk about now.
Great. So as Blake showed us, we can take measurements of the cosmic microwave background light itself, the CMB temperature and the polarization, and then we can then turn the crank on this procedure called the quadratic estimator to go from a map of the CMB to a map of the gravitational potential, right? So by locally looking for changes in the power spectrum of the CMB, we can stitch together a map of the gravitational lensing potential. And the key point here, as Dongwon told us, right, we have this high resolution measurement of the CMB. Because large scale lenses change the small scale CMB features, these are arc-minute deflections, you really need high resolution to measure this, and this is why ACT with our new high resolution CMB maps is really improving the fidelity of the lensing maps that we can make. Here you can see, shown in an orthographic projection, this is the new ACT Data Release 6 CMB lensing mass map that we made. This time we're showing it here as mass density or gravitational lensing convergence. The gravitational lensing convergence is proportional to the mass density, and so this map you can kind of think of as a mass map, essentially. This map covers a quarter of the sky. It skillfully avoids regions of the sky where there's a lot of galactic dust contamination. And I want to stress here that you can actually see the dark matter distribution by eye. The size of the lumps that you see here, those few degree scales, those few degree scale structures, they correspond to the peak of the matter power spectrum roughly around redshift 1 to 2 that Blake showed us earlier. Right, so you're actually seeing that dark matter dominated distribution by eye. To really see this pop out, we're showing you a zoom in of a 900 square degree region, now going back to the gravitational lensing potential instead of the convergence. And you can see the bright regions that are supposed to be the overdensities and the darker regions that are the underdensities. In the next slide, we'll show an overlay of the cosmic infrared background. So this is the distribution of dusty star-forming galaxies that make up the cosmic infrared background, the CIB, as measured by Planck. The red contours showing overdensities of that CIB and the blue contours showing underdensities. And you can see by eye here, there's excellent correspondence, both because of the fact that our mass map is extremely high fidelity. These are signal-dominated structures, and because the CIB and CMB lensing are highly correlated because their kernels peak at around redshift 2. If you flip back and forth, we can see this kind of correspondence, which is really neat to see. And you can see this across the 9,400 square degrees that we've mapped this out on. The next slide, we're showing a more quantitative way of seeing this. So the black curve here is this expected signal power spectrum, the theoretical power spectrum of the fluctuations in the CMB lensing convergence map. And then the dotted curves are showing you the noise per mode from various experiments, the blue one showing previous Planck lensing maps, and the red dotted dash curve showing our ACT map. So while our ACT map covers only a quarter of the sky, and the Planck map has a sky coverage that's roughly around 3 times larger, our signal to noise per mode is around 2 times better than Planck on the scales that on the regions of the sky that we reconstruct on. And of course, I want to emphasize again that as you can see with the x-axis on the top, where we are showing the co-moving wave number at redshift 2, corresponding to those multipoles, you can see that the reconstruction that we have is mostly on linear scales. You're going out to 0.1, 0.2 megaparsec inverse at most, but most of the lensing signal noise is coming from scales that are larger than that. Great, and then in the next slide, apart from measuring the power spectrum of that map, which Frank is going to talk about, the other really exciting thing that we can do now that we've made this map and we'll be releasing it to the community is that this mass map can be cross-correlated with a variety of galaxy surveys. So the community can now begin a campaign of cross-correlations to tomographically map out structure formation, sigma 8 as a function of redshift. But today we're going to show you constraints on S8 and S8 CMB lensing and sigma 8 from the power spectrum's mass map.
I guess another thing that you haven't explicitly said, and because I only just realized it, maybe other people aren't realizing it, because it's at redshift 2, the scales that are nonlinear are also deeper, right? Like it's not just the value of k that would be nonlinear today. At redshift 2, the value of k that would be nonlinear is even further into the small scales and large k.
That's true. And while if we had to pick redshift 2 there, we do want to emphasize that you still have a wide range of redshifts that are contributing, right? So we had to pick one to show on the x-axis there. So, most of the contribution comes from redshift 0.5 to 5, which is the redshift range that we'll mostly be referring to. But you're absolutely right that at higher redshifts, you have to go to higher k to get more nonlinear, right? Yeah.
you've got this kind of quadratic estimator that kind of integrates over all redshifts, and you, as you say, you talk about projected mass. Is there some way of there's more information hiding there that you could actually try and extract a redshift dependence of your signal by using different estimators? Or is it just like completely, the signal you're looking for is completely degenerate and you'd have to go to higher order statistics beyond the power spectrum?
We've discussed this internally, when we were looking at cosmological constraints from this map. So we observe one two-dimensional map, right? So with just that map, we can't disentangle the 3D information other than through possibly looking at the shape of the power spectrum itself. Because as Blake showed earlier in one of those plots, different redshifts contribute differently at different multipoles. And so if you could, in principle, try to isolate that information, but it ends up being highly correlated. I think we've tried this, and we found that it's difficult to do that because everything is projected into one measurement. But on the other hand, with cross correlations, of course, you can do this, right? With cross correlations, you can isolate the sigma 8 that comes from individual redshift sizes. You
mean cross correlating with, as you saw, CIB or other actual local measurements?
Let's say you have a spectroscopic sample, say from BOSS or DESI, and you have a thin redshift slice between 0.1 and 0.15, just as an example, right? And then you cross-correlate. You'll get a noisier measurement because you have noise from all the other redshifts, but you do get a sigma 8 measurement in combination with the galaxy clustering in that bin, right? So that's one of the many new measurements that there's ongoing work for with this mass map, and has also been done with Planck in the past.
Just one interesting, I haven't actually seen this plotted, but in the future with S4 we will have bispectra, and you can measure higher point functions even of this map, and that might be a way of getting redshift additional. That would probably have a different redshift sensitivity. So if you were just restricting to the CMB lensing map, that might be the one way, aside from scales, that you could try to get 3D.
That's right, because most of the nonlinearity would come from lower redshifts, and so you could disentangle that. That's a good point, yeah.
Yeah, you would think so, but I actually haven't seen this plotted, so this is like a bit of speculation.
Oh, sorry, I was going to say another avenue is that there's like these de-lensing techniques where you subtract scaled version of galaxy maps, and then you get access to higher redshift lensing, CMB lensing maps, or lower lensing add-on ones.
So I guess the follow-up question, if you're doing things like the power spectrum dependent extracting of redshift stuff, can you do that to at all kind of look at just the local low redshift and just the small scale to see what your best measurement is of the same statistic that these S8 tension finding people are measuring, so that redshift and scale? Or is it by that point you've just got S8 equals 0.7 plus or minus 1 or something ridiculous like?
Yeah, so we've done some preliminary checks of this, and it ends up being that you get something that either has very large error bars or ends up being extremely correlated with the original measurement that you made. But I agree that this is interesting to look at further. This is definitely interesting to look at.
Thank you, Matt. So in order to do precision cosmology, what we did is to build the state-of-the-art lensing power spectrum pipeline, where we can go from these lensing maps into an unbiased lensing power spectrum. And this pipeline requires several non-trivial but already standard bias subtraction steps to subtract these large biases that you get even in the absence of lensing, which will bias your power spectrum high. But perhaps the main challenge of this analysis is not about this pipeline, but given the high signal-to-noise we are trying to achieve, how we can really trust our results that it is free from systematics or other biases. And for this analysis, we follow a blind analysis procedure where we don't compare with theory or other data sets or look at parameters before we are sure that we are completely robust and free from systematics. And we were able to do many of these checks thanks to the huge redundancies that the DR6 data provides. So we were able to do like 200 null tests, which are broadly divided into the following categories. So if we're worried about foregrounds, we can check for consistencies between polarization and temperature, or across different frequency channels, or use different kind of foreground estimators, and also look for galactic foregrounds by looking at different sizes of galactic mass, for example. And we can do like signal isotropy tests by looking at different patches of the sky given our large area. We can look for potential contamination in terms of curl or other non like this B mode rotation that you don't supposed to get in your lensing measurements. We can isolate different scales of the CMB we use to do the analysis. And there's also a large number of instrument-related tests, such as maps built using different water vapor pressures at different times of the day, or other noise-only tests. So there's this whole array of things we do, and they're very important to just check for the main challenges. And I feel like the CMB lensing is already quite robust, given we know the redshift and the source, and that most of the matter causing this lensing are well described on the linear regime, where the Baryoniov effects are negligible for current measurements. There are a few key challenges, and these are related to whether for these ground-based measurements, these noise subtraction methods are good enough, and perhaps more importantly, whether we can keep foregrounds and extragalactic foregrounds under control. And Niall will talk about this in his part. And we also, DW led these extensive instrument-related checks about systematics using combinations of simulation and data, and found that for the DR6 signal-to-noise levels, those are subdominant for error budget. For a very long time, we were even failing the simplest of the null tests, where we just pass a noise-only map through the lensing pipeline, and rather than getting something consistent with 0, which is what you would expect given that there's no signal, we're getting these U-shaped failures. And that was just pointing that these bias subtraction steps are not working well enough. And we found out that the problem was that the ground-based measurements, the noise is very complicated. So here you can see the footprint we cover and the 2D noise at different regions of the sky. So it has a lot of structure, and it varies a lot from region to region. And that's due to the combination of the interplay between the atmospheric noise and also spatial inhomogeneities introduced by the scanning strategies.
When you say you pass noise-only maps through your pipeline, what is a noise-only map? Is it a simulated thing, or is there some way of extracting from the data something that you know is only noise?
Yeah, that's from the data. So we have a lot of different independent splits of data which have the same signal, so that when we subtract them one from another, the only thing you left there is the noise, and you should supposed to cancel the CMB signal there.
So if you look at the same point of sky today and tomorrow, then any difference must be not primary CMB, unless the primary CMB changes between today and tomorrow, which it probably should.
Yeah, that's right. Like any variability, we assume that's just due to the noise. And yeah, so like this problem stimulated a lot of development on the simulation front in the work led by Zach and Adri. But what really helped in solving our problems, and when we start really passing our null test, is when we start using a more robust cross-correlation based estimator. And the idea of this is very simple, where rather than just passing the same CMB map through our quadratic estimator to find the lensing power spectrum, we use 4 CMB maps that have independent noise. So they are like chunks of data collected at different times, and that they're separated long enough so that the noise is independent. And this way, when we pass this through the estimator, the noise part cancels out. And it's nicely illustrated here that now using this estimator, instead of this U-shape, you get something consistent with 0.
And did you work out what was going wrong with the previous thing? Or is it like now obsolete, it doesn't matter, there's nothing to be concerned about?
The main thing seems that there's like these complexities in this noise modeling, that they can give you some non-trivial trispectrum induced by the noise. And having better simulations actually makes just using the naive quadratic estimator better. But we found that using this method, we are much more robust to noise modeling or other details of regarding the noise.
Yeah, so I'll just say a little bit about what we mean by foreground in CMB lensing. So the issue is, of course, that CMB photons come from the last scattering surface, and as they make their way to us, they're lensed, but they're also scattered by hot gas in galaxies and clusters. So that we know that as the Sonia-Zeldovich effect, and they're joined by other photons from dusty galaxies and AGN and such things. And this is all really cool astrophysics, but for lensing, it's foregrounds. And we need to make sure that any imprints of this astrophysics is at a very low level, given we're trying to make a 2% measurement here. So just to get a little bit into the theory here, we can just sort of think of these foregrounds as imprinting at, perturbing the observed CMB temperature a little bit. That's the TFG on this slide. And so when you substitute this total temperature into our estimator for the lensing power spectrum, which remember it's a power spectrum of a quadratic estimator, so it's 4 temperature fields basically going into this lensing power spectrum, you get a whole load of bias terms. You get what we want, so that the term we want is the true lensing signal, which just depends on TCMB. But you get all sorts of extra bias terms as well that come from the fact that these foregrounds are also non-Gaussian or statistically anisotropic, and to some extent those anisotropies is what we're trying to measure as lensing. This is not terrible because these things don't really look like lensing. And it kind of goes back a little bit to your question about could the primary CMB look, just be weird enough that it looks like lensing. And it would have to be super weird for the type of non-Gaussianity there to look like lensing. And certainly extragalactic foregrounds don't really. So they look like blobs and point sources and that sort of thing. The kind of mode coupling they generate is very different to what's generated by lensing. And so that motivates various strategies. So we can use match filter approaches to find sources and clusters. We use this method called bias hardening, or we're calling it profile bias hardening. That's been around a while. It's sort of, again, saying that the statistical anisotropy generated by these foregrounds doesn't look like what you get from lensing, but it's sort of making that statement in mode coupling language. So the correlation of Fourier modes caused by the presence of these foregrounds is quite different to what you get from lensing, and you can basically deproject out the type of mode coupling you get from these point sources and clusters. And then the final thing we can use is the frequency dependence of foregrounds. So for most of the analysis here, we're just using 2 of the frequencies from ACT. This doesn't give us a whole lot of scope for deprojecting foregrounds. Future data sets will do that more, but we did test some variations of our analysis with incorporating extra frequencies from Planck just to make sure things look consistent. I've sort of confidently talked about the mitigation strategies. How do we actually test this? So the first thing we do is look at a couple of microwave sky simulations basically and just run all these mitigation strategies on there. That's what this plot shows. This is the fractional bias on the signal as a function of scale. If we just find and mask sources and clusters, point sources and clusters, we get the purple line, biases at the few percent level. In the legend there is the bias on the amplitude of the signal. If we additionally use this bias hardening method, that gets us down to the percent level. And this sort of is another sort of summary plot. This is the bias in the amplitude of the lensing power spectrum as a function of the maximum scale we use in the lensing power spectrum. So these things tend to get a bit worse on small scales, these foregrounds, and so by using a sort of conservative maximum L or minimum angular scale, we can reduce the foregrounds as well. And so the grey region here shows scales that we didn't use in our baseline cosmological results. But even if we had gone up to sort of L of 1300, and we did show these results in the paper as well, the biases in the lensing amplitude are still like a quarter of a sigma, so not really anything to write home about anyway. This is from 2 different simulations. So as well as that, Frank already mentioned we had a load of tests on the data. You can basically construct null tests that should be sensitive to foregrounds because of the frequency dependence of those foregrounds. And I mentioned we also incorporated some Planck data and tried deprojecting foreground SEDs, in particular the CIB, and made sure that we got a consistent lensing power spectrum.
So you said deprojecting foreground, and then you said some acronym?
Oh, right, yeah. So when you deproject a foreground, you need a model of a spectral energy distribution for that foreground. And so the one we were trying to deal with was the cosmic infrared background, for which we know a approximate spectral energy distribution. It's like a modified black body, basically. And so yeah, if it's basically good enough to get the CIB to a pretty low level. Yeah, so when we do that, we still get consistent results with our baseline. So it reassures us that the cosmic infrared background is not an issue for us.
yeah, you used Planck as a kind of independent measurement. I guess because they've got more frequencies, this SED is easier to use for them. I guess perhaps the answer to my question is that you've shown it's just not that big a deal, but in principle you could have actually used other measurements of the CIB and other extragalactic stuff to predict what their size should be to be able to extract them, but maybe that's just not necessary, because if it's a quarter of a sigma, then who cares? or at least there's other things to worry about first, and maybe 12 months from now a new paper will come out where that's been done and it got improved by a quarter of a sigma. Is that essentially the answer?
Yeah, I think we definitely like to explore that sort of thing. I guess we were kind of keeping it simple here. There's other complexities in bringing in other data. For example, we talked about having this cross-correlation based estimator, so we needed the ACT data and 4 independent splits, and we didn't have that for Planck, for example. We also were a bit worried about galactic dust, so you get a really statistically powerful estimate of the CIB from using high-frequency Planck data, but then that might also be affected by galactic dust, and you might end up not modeling that correctly. So there were some potential complexities with incorporating the Planck data, but yeah, in theory, using more frequencies in the future will definitely help this further. And that 0.25 sigma for us, for SO, will be more of an issue. So yeah, we will need to improve.
Thanks, Neil. So just to recap, there were 2 main challenges for these ground measurements. So one is whether we can subtract the noise biases accurately enough, and we solve this using these cross-correlation based estimators. And the worry about foreground mitigation, Neil showed that using profile hardening, we can keep them under control. So using these 2 methods, we were passing all our null tests. So we're just showing one example here. So this is the scale-based null test where we change the scales of the CMB used for the reconstruction. And as you can see, the shift in the lensing power spectrum, they are very consistent with the baseline. And this is a very non-trivial test to pass, because changing the small scales of the CMB used, we're exposing ourselves to different levels of extragalactic foregrounds. And on larger scales, we are testing our reconstruction on different instrument-related effects, such as transfer functions or galactic foregrounds. And the fact that they're very consistent shows that we have them under control.
What does aggressive Fourier mask mean?
So this is for ground-based measurements. We are also applying a Fourier space filter on the horizontal and vertical modes, and that's to remove contamination from things like ground pickup. And we can change the size of this filter to check that we have all the contaminations mitigated. So these ground pickups, due to the scan strategies, they are very localized in Fourier space, and we can just mask them appropriately. So similarly, we obtain these consistent lensing spectra for the different null tests. And just to summarize those, I show here this shift in the lensing amplitude compared to our baseline. And as you can see here, they're all very consistent with 0, showing that we are robust in tests that checks for measurements taken at different times, using different polarization channels, different foreground mitigation methods, different frequency channels, different patches of the sky, and the scale-based test, and many more. And this shows that our measurement is robust, and we can go and look for the cosmological results.
What exactly is a lens here? Is it just a complete rescaling of the entire lensing potential with all cosmological parameters remaining constant, or is it like a new fit where cosmological parameters could change and then it's some average amplitude, or what is it?
So that's essentially just we parameterize our lensing power spectrum with this one single number as just amplitude shifts. So that's just compare that with a given fiducial lensing power spectrum without changing the parameters, the cosmological parameters.
Okay, so there's some fiducial set of cosmological parameters that would give you a particular shape of lensing potential, and then you multiply that by a lens, and it would just scale it up or scale it down. And
a statement is that generally just the amplitude of the spectrum contains most of the information. So if you want to get a shortcut for checking how much a particular systematic matters, that's a convenient way of doing it. You just have a fiducial spectrum and you say how much does the amplitude get shifted up and down by a certain analysis variant or a certain systematic.
Okay, so in terms of cosmology, so here I'm showing just the theory spectrum as predicted from Planck that we use to compare our measurements. And here's just a snapshot of the unblinding event that happened a bit like a few months ago. And now, like, just going to our measurements. So you can see visually that our measurements without any free parameters, they agree very well with the underlying theory that we used. So, which is the black line here, which is the predictions based on the Planck 2018 CMB power spectrum, which is not a fit. So you can see this agreement very well by eye. And we are determining this amplitude lensing at 2.3% precision. And in our baseline range we use, which is given by this white region, we obtain a signal to noise of 43, which is the state of the art alongside with Planck, which achieves a signal to noise of 42. So this range has been determined before unblinding just due to our null test and foreground checks. And in retrospect has been a bit conservative, and that's why we as a report result in a more extended range given by this light shaded gray region. Furthermore, we also measure this using the polarization only data without using temperature, so that we get an independent measurement using polarization, and that's given by these blue measurements, and that's also consistent with our baseline and with the predictions from Planck. It's worth mentioning that with polarization alone, that's the most precise lensing measurements of its kind to date. So almost doubling the previous measurements. And putting our measurements into context with the other CMB lensing measurements of the field. So what's nice is that given that we are measuring the same observable, we can all put them in the same figure. And you can see that generally they have good agreement between each other. And our measurements in red is the state of the art, along with the latest measurement from Planck in blue. And it's also kind of remarkable that these state of the art measurements happen really fast in a field which has been rapidly evolving, that you can see this even using ACT alone, that 10 years ago, we barely made like the first detection. And now we are evolving to this state of the art measurements that allows us to get very strong cosmological constraints. So back to precision cosmology, using CMB lensing alone, we report this best determined ACT CMB lens parameter, and we measure that at a precision of 2.7%. Here you can see the blue contours of this degeneracy direction. How do we compare with the 2-point predictions, like the extrapolations from the CMB? So perhaps not surprisingly, given the agreement on the lensing power spectrum level, we agree very well with these extrapolations from the CMB. So that's shown in the orange contours for the predictions from the Planck 2018 CMB and isotropies, but also completely using like almost independent data, we also achieve good agreements with the ACT DR4 plus WMAP CMB 2-point predictions. The comparison is not just limited to Planck alone. So there's one further thing we can do using lensing alone to improve our constraints further. So here is the lens shifting map as seen by the ACT DR6, and here is the Planck lensing map. And they both contain significantly independent information. So given that one is a space mission and one is ground-based, they have different noise and instrument-related systematics. They have different sky overlap, and also they probe slightly different angular scales. And furthermore, given that the individual CMB lensing measurements itself, they are very consistent with each other, as shown here, the blue ones for ACT, and the gray one is the Planck M-pipe reanalysis. We can combine them, and that's what we do at the likelihood level. And we do this in a consistent manner, accounting for the partial sky overlap in scales and in area. And we compute the covariance matrix using the simulated CMB lensing reconstruction simulations for ACT and Planck to get the covariance matrix and have this joint likelihood.
Plots like this always raise a mild red flag concern in the back of my mind, which is that they lie directly on top of each other. If there is actual statistical noise, you actually expect them to be roughly half to 1 sigma apart. Of course, if you show enough contour plots like this, eventually you'll get to that look this much on top of each other. So maybe, I should not be too confused or red flaggy, but does it not alarm you a little bit that they're so identical and that it suggests that there's something funny going on? Or
I think it's partly just a visual thing. Like the central values are not that similar, right? In the box there.
oh yeah, that is half a sigma different. Yeah.
Yeah, I think you just have these super long contours, and it's hard to see where the 1 sigma is. But there's a bit of a shift.
Yeah, so they do share like even though they have like so much independence, we need to like account for this overlap in area and also this overlap in scales. And when you propagate them and calculate the covariance matrix, there are like some band powers which are correlated at most at the 40% level. So that's taken into account when we propagate it to the likelihood. And if we combine them, the optimal lensing combined constraint is given by these red band powers, and that gives 2.2% measurements from a single weak lensing probe alone, and that's like the state of the art for CMB lensing, and also very competitive to the other weak lensing probes. Yeah, so what does our results tell us in terms of implications for structure growth? Perhaps we're very excited, and in our opinion, this is a very great success for the lambda CDA model, because we need to be aware of all the physics that need to go right for this agreement to happen. So we first need to fit the Planck CMB at early times at redshift 1100 and predict how the structure is going to look like at low redshifts, and also predict the lensing signal which arise over these right random redshifts and the trispectrum or the 4-point function it gets on the induced on the CMB. And then we go on and measure this with the independent experiments from ACT, and we agree at the 2% level, and we don't find a signal which is low. And given that we also agree very well with the Planck lensing and the CMB, it suggests that there's not evidence for systematics on the Planck measurements. And also, our measurement is much more sensitive to high redshifts and large scales, and therefore this favors new explanations physics explanations that change the structure growth at those regimes. But it's very interesting to compare with other weak lensing probes or things happening at lower redshifts or smaller scales, and that's why combining with external data sets with BAO is interesting, and Matt's going to tell you more about this.
You're using Planck in-pipe, is that because they've got their various different map making things? Is in-pipe just like what you're supposed to use in 2023, or is there some reason why you're using that? I presume with the other maps, broadly speaking, everything you're saying is going to be unchanged.
Yeah, I think it's like the cosmological implication is mainly consistent. It's just this M-pipe is the latest analysis, and they have squeezed in more CMB data, so that's the most constraining results they have at the moment. Yeah, I think it improves the signal to noise from 39 to 42 for their measurements compared to Planck 2018.
All right, great. So as Frank just showed us, we have this amazing measurement of the CMB lensing power spectrum and the cosmological constraints on the S8 CMB lensing parameter, sigma 8 times omega m to the 0.25, which is perfectly consistent with the Planck primary CMB early universe extrapolation, right? And so we want to emphasize again that this is a measurement of CMB lensing mostly from redshifts 0.5 to 5 and linear scales, and that measurement of structure formation is not low compared to the Planck CMB and isotopy prediction. Right, so we measure this combination sigma 8 and omega m to the 0.25. That's the best constraint direction here. You can see that the contours in red from ACT CMB lensing. However, in order to make our comparisons with galaxy weak lensing or cosmic shear better, and you can do something even more powerful where you combine with baryon acoustic oscillation measurements from SDSS and BOS and EBOS mostly. And so when you do that, as you can see on the next slide, the slice from the BAO in the gray dash contours gives you this nice round contour in sigma 8 in red, here shown with ACT CMB lensing plus BAO, also shown as the Planck CMB lensing measurement from a couple of years ago in combination with BAO. And this gives you a really tight measurement, a 1.86% measurement of sigma 8 itself. And that measurement of 0.819 plus or minus 0.015 is, again, perfectly consistent with the Planck CMB early universe extrapolation. And on the next slide, what we do is as Frank showed, since these measurements are consistent, you can combine the two, and you can use both the ACT and Planck CMB lensing measurements together, properly accounting for their covariance, and then you get an even tighter measurement, a 1.6% measurement for ACT plus Planck lensing. So now what we can do is we can start to do a consistent analysis where we take the same BAO data set and we add it to other galaxy weak lensing measurements to do an apples-to-apples comparison. What do different probes of the matter distribution tell us about sigma 8 when we add BAO to it to break the degeneracies and make a comparison? On the next slide, that's what we do. So here we show various galaxy weak lensing measurements shown in bluish, purplish colors, again combined with BAO. And the first thing, of course, you'll notice is that many of these measurements all of them are a little bit low. Not individually, they're not in any significant tension, but they're all kind of consistently low. So the two measurements from HSC Y3 from a couple of weeks ago, both the real space and Fourier space measurements, KIDS 1000 and DES Y3, they're all a little bit low. The other thing you'll notice here is that this combination of BAO gives you a much tighter constraint from CMB lensing. The constraint from galaxy weak lensing or cosmic shear seems to be not as good when you combine with BAO. And we can talk about this later, but the short answer here is that CMB lensing probes a wider range of scales. So we essentially have more than just one power law measurement, and so we break a degeneracy in the H0 direction. Being able to distinguish the shape of the power spectrum better allows us to break a degeneracy in the H0 space, which is not shown here. And that leads to a tighter constraint on sigma 8. The next thing we can do is look at 1D marginalized posteriors for sigma 8 and also for S8 itself. So as I mentioned, that the constraint from sigma 8 is not as good on the galaxy weak lensing side. So instead we pick the S8 parameter, which both CMB lensing and CMB lensing measure reasonably well. So on the left side you see sigma 8, and on the right side we see S8. So we choose the S8 space to be where we quantify the tension between these different data sets, because that's the space where things are reasonably well measured. And here, I think you can see it's pretty stark now. The green measurements are the Planck CMB and isotropy, early universe extrapolation. All the others are late universe measurements, but the red ones are all the CMB lensing measurements at probe redshifts of 0.5 to 5 in linear scales, and the blue ones are all galaxy weak lensing measurements at probe redshifts less than 0.5 and smaller scales in the matter power spectrum. They're all around 1.7 to 2.1 sigma lower than CMB lensing, and up to 2.7 to 3 sigma lower than the Planck CMB and isotropy measurement. We can come back to this in a bit, but I want to show a couple of other things that we can do this really high precision sigma 8 measurement. So on the next slide, we can also weigh in on the Hubble tension, and this is because our CMB lensing measurement also depends on the Hubble constant, as I just mentioned, as a degeneracy. We can now combine it with the BAO measurement to break a degeneracy between omega m and H0 that the BAO dataset, the galaxy BAO dataset has. And when you do this, you get a tight 1.8% measurement of H0 from the combination of ACT lensing and BAO and BBN. But this measurement does depend on the sound horizon, and from the many talks you might have had on Cosmo Talk about early dark energy and possible resolutions to the H0 tension. This is interesting. So our measurement that does depend on the sound horizon is consistent with the Planck primary CMB measurement and discrepant with the Cepheid calibrated supernova measurement at 3 sigma. However, what we've done here is to use a new technique from that was proposed by Blake Sherwin and who's on the talk right now, and Eric Baxter and others, where instead of combining with BAO, you just break the omega m degeneracy by combining with Pantheon supernovae. And then you effectively use the matter radiation equality scale and redshift that's imprinted in the matter distribution. So part of this information is coming from essentially the scale of the lumps that you saw, using that as a standard ruler. And then you get a measurement that is independent of BAO and therefore independent of the sound horizon. Right? And we see that that's also low, right? So we see that measurement is also low compared to the Cepheid calibrated supernovae. So it's consistent at the 2.5 sigma level, right? So we can't, if it is more precise, then you could potentially say that this is putting certain theories that try to modify the sound horizon physics in order to resolve the Hubble tension, putting those theories in a bit of trouble, right? So we're not quite at that stage yet, but it's interesting to see that we can make these measurements using lensing of a measurement of H0 that's independent of the sound horizon.
Can I just maybe slightly unpack one thing? So other than this kind of bottom of the red ones, or maybe the one above it as well, actually, the ACT lensing was getting information about kind of distances or expansion rates via the kind of combination with the baryon acoustic oscillations. But then there was this new technique that is essentially saying, I guess, how the peak of that matter power spectrum, where it is, relates to this matter radiation equality scale. I guess analogously to the first peak of the CMB anisotropies giving you information about H0, this is now doing the same thing in the lensing power spectrum. So that's then got nothing to do with the sound horizon. It's where the peak in the matter power spectrum is. Interesting.
Yep, that's exactly right. Great. And then one last thing, the one exciting thing that we can do with neutrino with the sigma 8 measurement is if you see a certain amount of clumpiness in the late time universe, then you can compare with the clumpiness that you predict from the primary CMB measurement. So in order to do that, we combine our lensing measurement with the Planck primary CMB measurement. And that allows you to translate the observed low redshift clustering amplitude to a suppression that's caused by something, say, like massive neutrinos. Right? And so we use that to get a very tight constraint. In terms of Fisher information, this is one of the tightest constraints on the sum of neutrino masses. And you can see here that it improves over Planck lensing by around 15%. And if you do not include lensing but only uses primary CMB and PAO, it improves on that even significantly. And this constraint on the sum of neutrino masses of 0.12, you should compare it to the inverted hierarchy minimal neutrino mass, which is around 100 millielectron volts or 0.1 eV, right? So this is, one of the best ways of measuring neutrino masses, and in the future we'll have even more precise measurements that'll help us get to the point where we can start potentially ruling out the inverted hierarchy or detecting neutrino mass in the next 5 to 10 years. Okay, so we'll leave the summary slide here, which shows again that the exciting fact that we've measured CMB lensing, which probes redshift 0.5 to roughly 5, and we get an answer that's consistent with the primary CMB measurement from Planck and ACT and other measurements.
So what comes next? Now that we know the S8 results from ACT lensing, and perhaps that it's not intention at all, and I guess that's a potential scale and redshift dependent thing. How can we get more information, and what comes next?
So what we have here in terms of the outlook for the S8 tension in particular, as Blake showed in the beginning, there was this nice this compilation plot that shows in green the Planck primary CMB extrapolation for what S8 should be, and in blue the low redshift nonlinear scale, mostly nonlinear scale measurements of S8. And what we're seeing is that the CMB lensing measurements that probe redshift 0.5 to 5 and linear scales are consistent with the early universe prediction, and probes of redshift less than 0.5 and smaller scales generally fall lower. So we think there's a new outlook here that we really want to motivate new comparisons, not just between the primary CMB anisotropies and the large scale structure in general, but rather kind of maybe hone in on this. Either it's a large scale in the matter power spectrum versus small scales in the matter power spectrum issue, or something maybe is happening at less than redshift 1 or less than redshift 0.5, right? So I think there's a program here of trying to disentangle whether it's redshift dependent effects or scale dependent effects. So scale dependent effects could include something annoying like baryonic feedback, or it could include something really exciting like new axion dark matter induced suppression of the matter power spectrum. Redshift dependent effects could include modifications to gravity or non-standard dark energy, or it could be a mix of these things, right? So that's one of the things I think really to look forward in the future is that we should make more of these measurements, the blue and the red, and the green as well to get tighter, but especially getting between the red and the blue, CMB lensing and weak lensing, and also as DW will mention in a bit, the mass maps you're putting out allow us to do a part of this program, right? So they let you cross-correlate tomographically. As you can see, these CX measurements here at the bottom are cross-correlations of CMB lensing. With galaxy surveys, if you restrict those to linear scales, then you can disentangle scale-dependent effects from redshift-dependent effects, for example. So there's lots of exciting avenues in the future to kind of really get at the heart of what's going on here.
Yeah, I think one of the annoying things about this is that all of the individual probes of these like kind of blue ones are not statistically significant enough that they themselves can be broken up into Z and K space and still see something interesting. But maybe combined, there is something interesting. But what you ultimately want is a Z/K 2D measurement of S8 to see how it is and isn't intention at different values of Z and K, but it's difficult to do that in any individual experiment.
These things will get better.
Mm-hmm. That's right. I mean, so combining is tricky because there are different experiments. There are brave people attempting to do it. But at the same time, Rubin Observatory is going to start observing this year, right? And the KIBS has another data release. I think DES will have another data release, HSE possibly as well. So things we'll start getting more data. So on the blue side, we'll get even better measurements. And ACT, we've only analyzed half of the data. So DW is going to tell us more about the next data release, right? So before we even get to Simon's Observatory, there's more stuff coming.
So now I'm going to talk about the future of CMB lensing science with the ACT collaboration. So for the near future, there are a number of cross-correlation projects that leverage a high signal-to-noise ACT DR6 lensing map. So as Matt had mentioned earlier, ACT has overlap with a number of leading LSS tracer, as you can see on the plot on the bottom right. And by cross-correlating CMB lensing map with this large-scale structure tracer, for example, galaxy density, we gain access to the 3D tomography information of matter distribution. And this allows you to probe the science that are not accessible to either probes alone. For instance, you can probe the structure growth as a function of redshift. You can test the theory of gravity over the cosmic scale, or you can probe the astrophysics at very high redshift. So in the below, I have listed some of the projects that are already in progress from the ACT collaboration, and some of them are very far in progress already. So I just quick advertisement, it's paper. Look out for them on the archive. We are very excited to share the result from this project with the wider scientific community. Another piece of advertisement that might be interest to the wider audience here. As Matt has mentioned earlier, this ACT DR6 lensing map itself will be released upon the publication of the 3 papers. So if you have your favorite LSS tracer, as we are do, you can take our DR6 lensing map and cross-correlate it yourself. Also, our lensing likelihood is already available. So if you want to add our ACT lensing likelihood to your parameter constraint, that's already possible. So if you're interested, please take a look at the webpage below.
And if you're the reviewer in charge of reviewing these papers, then you have a moral duty to be as fast as possible so that this data is publicly available. Although not neglecting the due diligence of making sure everything's correct. You don't want to release these public data things until you're confident.
Everything is correct, so we should be fine. And lastly, so there are still room for improvement in terms of lensing map. So as I mentioned earlier, there are still the daytime data, which is about one-third of our total data volume. And there's additional season job data from 2021 to 2022. So on the plot on the top, I'm showing the expected improvement as a noise to the lensing order spectrum. The current expected noise level is showed as a dotted curve there. And as you can see, the largest improvement is at the smaller angular scale. So with this improved lensing map, we'll be even more sensitive to the small scale matter distribution, which helps the science case, such as some of the neutrino mass or axion physics. So that'll be exciting. And furthermore, we can still improve our analysis choice, such as how we filter our data, the detail of our estimator, cross estimator that Frank has mentioned earlier. We can combine our ACT data with the Planck data at the map level and make optimal lensing reconstruction combining both data sets, which is going to be optimal lensing reconstruction. So combined with all this improvement, in summary, you can expect more great lensing science from the ACT collaboration, hopefully in the very near future.
So I had 2 remaining questions that I didn't ask at the time. I guess one of them is you guys have this excellent measurement of the higher redshifts, more linear scales compared to, say, cosmic shear. Is there anything else out there that is already done that is also at a higher redshift? Like is Lyman alpha stuff also higher redshift, larger scales, measuring S8, or are they somehow not measuring S8 for some reason that I'm not aware of? I guess someone at some point had these 2 like colors, was it blue and red or something, and you want the kind of purple in between. But have such measurements already been made that I'm forgetting about, or?
Yeah, I think that they're also at high redshifts, right? The Lyman alpha 1D power spectrum measurements, but they're very small scales, right? So there's a plot I was showing, but yeah, those are also very interesting.
Do they have S8 tension or not S8 tension?
I need to look this up actually. I don't remember them being dramatically in tension, but these are also those are extremely powerful measurements in the sense that they're probing really small scales, but they're also they're also a little bit challenging because you need to simulate the state of the IGM and stuff like that. But I think people have done lots of work and are working very hard on this, and so yeah, that's also going to be an interesting angle.
And like the largest scales of galaxy clustering measurements are not large scale enough yet. Is that a fair thing to say, or?
I think this plot is it's a pretty rough plot, but it's not that far off. So I think there is some overlap in the galaxy clustering with the CMB lensing measurements, and similarly, probably the largest scales in galaxy lensing kind of overlap with our smaller scales. So they're not completely distinct. But
the other question I think related to this idea of the matter redshift equality distance scale. Matter radiation equality is a time, but then there's a distance scale, which is the horizon, and that puts a feature in the matter power spectrum, which is then used to infer H0. Matt did mention that, stuff that tries to change the sound horizon won't change that. But I guess that's not completely true. If you have some sort of funky early dark energy model, it is also going to change the matter radiation equality scale. It's not going to change it in precisely the same way, but one could conceive that something that fixes the H0 tension with some early universe change and expansion history would potentially affect both of those two distance scales. I don't know, in the right way, such to solve the H0 tension. Not that anything has actually solved the H0 tension without. I mean, that's kind of the theme of the cosmology talks we've had, is that it messes up the S8 tension if you fix the H0 tension. But is this a fair thing to say? That
I think the most basic thing that you can say is that you would expect it to change the two scales in a different way. Right? I mean, there's no reason for them to be changed in exactly the same way, given that there's some, order 10% change in the energy density, in the composition of the universe happening. That's quite, kicks in and dies away quite rapidly at redshifts of a few thousand, right? So it would seem a bit strange that for no reason those scales were messed up in exactly the same way and gave you the same wrong answer, right? But there has been some work at looking at this quantitatively with these sort of sound horizon free measurements, and I think it the exact sometimes it sort of depends on exactly what data combination you're using, and it does seem like sometimes it's not affected at all, but sometimes it is a little affected, and I think a little bit of a problem right now is that when you add more free parameters in these EDE models, for example, the error bars tend to blow up. So if it's 3 sigma low, then suddenly it becomes 2, But I think in the future, when these measurements get more and more constraining, if these error bars shrink by a factor of 2, then if we still come in low, that I think will be very interesting. And I think you'll have to say, both the sound horizon and the equality are messed up in the same way for no reason at all. I mean, I think that'll be very powerful.
Although something that would be really cool and would indicate that it is something early universe would be if they got messed up differently. Like if sound horizon came in at 67 and matter radiation came in at 70 or something, but both statistically significant, then it's like, okay, well, that's super interesting evidence that would be exciting.
Yeah, and I think we've only just started looking at like what exactly these signatures would be, for how things would be messed up.
Cool, thanks everyone. What the last question for whoever feels like taking up the baton, what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
One answer would be just that, working in these collaborations, I don't think a lot of people realize just how much sort of infrastructure work and low-level analysis goes into making these science analyses happen. I think people who are in the collaborations know that there's all this heroic work going on and sort of map making and like data quality checks and beams and simulations, and I feel like sometimes, and that's the same is true in large scale structure and generating the catalogs, and I think sometimes those folks don't get quite the visibility they deserve. I mean, I think most people know this, but I think that's important. But I guess more in terms of the S8 tension, I think what maybe is appreciated, but I think should be appreciated even more, is I think if we take this seriously and we think maybe this is a sign that there's something going wrong on small scales or on low redshifts, I think just work to exclude the more prosaic explanations, like excessive baryonic feedback, I think will be very important. So, for example, using SZ measurements to exclude the fact that what we're seeing here is that, it's an interesting explanation, but it's not as interesting as new physics. Just that AGN, or, the feedback is stronger than expected. So just homing in on the explanations that are not new physics and ruling them out with SC measurements, KSC measurements, things like that, I think will be very interesting, because the burden of proof should be quite high.
So one of the underappreciated things, I think, is that DESI is making measurements of galaxy clustering at this moment, and they already have data that's better than BOSS, right? Significantly better than BOSS. And so if you go back to the neutrino mass slide, we do have a degeneracy with omega m. The neutrino mass measurement is degenerate with omega m. The full DESI data release could potentially get this measurement just with this particular ACT lensing measurement. The 1 sigma constraint could come down to 40 MeV or 2 sigma 0.08, right? So I think that's an underappreciated fact that DESI is making these amazing measurements that will help existing structure formation measurements, including CMB lensing, get much better constraints on neutrino mass, because we have a degeneracy of omega m. So these public likelihoods that we put out will enable that kind of really good neutrino mass measurements.
Cool. Thanks everyone for watching. If you liked the video, subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, both to help yourself and help the channel, because YouTube will know to recommend more stuff like this to you if you click like. And share the channel with colleagues. Maybe check out another video. I'm going to suggest one from the early days of Cosmology Talks, which was Omar Darwish talking about, if I remember correctly, using the TSZ effect to, or removing the TSZ effect, using non-CMB measurements to remove the TSZ effect from these lensing maps. Can't make any promises about the quality because it was 3 years ago, but other than that, thanks everyone for the great talk.